So, well, today we're going to continue on with the definite integral. So, let's just try to quickly recap what it is we know so far. So, in the process of trying to compute the area under a curve on some interval a to b, we decided a good idea would be to build little rectangles under this curve, right, and to add up the area of the rectangles. So when we did that, we add up all the areas, okay, and so these areas look like, well, you have the width of a bunch of rectangles times the height. The height, of course, actually we chose some c. So we divide it up right in little intervals. We choose c's in the middle of each of these little intervals. Okay, and we add these things up. And we start with n of them. And this gives us an approximation of the area. And then we take the limit, and as the number of these rectangles goes to infinity, and of course, as this is happening, right, the width of each of the rectangles is going to 0. And so this, right, was our expression for the area under that curve. And then, because it was, a lot to write this down every time, we decided to write it like this, or sometimes like this. When I say sometimes, I mean in the literature always. Okay. And then we proved a remarkable fact. It was the fundamental theorem of calculus. And the fundamental theorem of calculus said if f is continuous on an interval a, b, and mind you, the reason why we want continuous is what? If the function is continuous, what do we know? Something about this limit. If the function is continuous, then the limit exists. Okay? Of course, limits don't have to exist. If this limit doesn't exist, then we don't have this. Right? We don't know what we're doing. We say the function is not integrable. Right? But if the function is continuous, then the function is integrable. This limit exists. Okay? So if f is continuous on a, b, then the integral from a to x, right, where we choose x as our variable. Okay, we're fixing a variable x. However, we're not fixing, we have a variable x, right, which, well, being a variable, can vary. So we have this function, all right, we call this g of x. And what we proved is that if you take the derivative of this function, right, well, you get the function x. So remember, this was the function that, right, you lay down the paper over your transparency and you start pulling it across, right, you reveal more area. Okay, so as x would grow, right, this reveals more area. Okay, that's a function, you take its derivative, and we got that. And we called this function here g of x. Okay? So today, we're going to start by proving part 2 of the fundamental theorem of calculus. Okay, so FTOC, FTOC, fundamental theorem of calculus. But I like that. Part 2. So, all right, we keep the same hypotheses as before. We let, I'll just write it, let f be an antiderivative for little f on AB. Okay, take any antiderivative we want. Let's say we want to compute this integral. The second part of the fundamental theorem of calculus says, and this is what you've taken calculus before you've probably seen, is this is equal to, well, you evaluate the antiderivative at the larger endpoint, and you subtract the antiderivative at the smaller endpoint. And this is really quite remarkable. It just says you have to do this antiderivative and evaluate it at 2 points. Do the subtraction, boom, you've now computed an area. So in essence, the antiderivative, which we built to solve differential equations, is also independently useful for solving area problems. This is really quite something. All right, so let me rewrite this using 2 bits of notation, which are more standard. And this will be our little formula here. So typically, of course, they write the integral over the interval not with the integral under the integral sign, but actually putting what are called, these are called the limits of integration. They put them up here. Okay, this is how it's normally done. Okay, I only do this to motivate notation later on. So, but for now, we're going to switch over to this notation. And, of course, it still says this integral is equal to f of b minus f of a. But there's another bit of notation for this. When you want to evaluate a function at 2 points and then subtract, right, your answers, the way you write this is f, then you draw a vertical line, and you put the one you want to start with on top and the one you want to end with on the bottom. Okay, so this is just notation. So use this little colon next to equal signs and define it this way. So this is our, that's the formula. Okay, let's prove it. The proof is very easy now using part 1 of FTOC. And the reason why is this. We said let f be an antiderivative. We already have an antiderivative for f, though, by the fundamental theorem of calculus. What is the other antiderivative for f that we have? Remembering, an antiderivative is a function whose derivative is f. So what function do we have whose derivative is f? Now we have this function which we call g of x. Right? So f of x, or f here, is an antiderivative, and so is g. Okay, so I have 2 antiderivatives. What do I know about them? Do they have to equal each other? Up to a constant. They have to equal each other. Yeah? All right, so we know that g of x can be written as f of x plus c, since g prime and f prime both equal f. Okay, this was the very first. Somehow we have to get b and a into the game, right? Because that's what the formula looks like. So let's try plugging the a in. So let me out a little space here. Just remember, what did g of a equal? So g of a means you put an a in for x. So you integrate over the interval a to a, which we actually define to be something very specific. 0, right? Remember, this thing is computing the area under a curve where you only look at some of the area, right? You cover up some of it. Okay? And when you only go to a, that means you're covering up everything but that first line. Of course, the area then, you have just a 0 with a rectangle, right? It's 0. So this is 0. On the other hand, it's equal to f of a plus c. So what does c equal? C definitely does not equal 0. C equals negative f of a. Right? F of a plus c is 0, so c is negative f of a. Okay. So instead of writing this top expression, I now know that g of x equals f of x minus f of a. Okay, but I'm not interested in g of x as a function. I'm interested in this integral from a to b. Okay, so what is that integral from a to b? Well, that's exactly what I would get if I put a b in for x into my function g. So actually, this is g of b. If you look back in your notes, you'll see right after we defined g of x, we wrote down what g of a equals, it was 0, and what g of b equals, it was this. Now, by the above formula, g of b is equal to f of b minus f of a. And so the integral from a to b of f of x dx equals f of b minus f of a. Finishes the proof. Questions? Doesn't seem that complicated. Of course, why does it not seem that complicated? Well, we've built in all of the difficult stuff. Right? The g of x being an antiderivative, that two antiderivatives differ by a constant. All that hard stuff was done before, so now we just get all the easy stuff. There's a group of mathematicians who, for many, many years, have written these books under the name Bourbaki. And they have a very distinct style, and part of their style is to take all these difficult things and put them into the definition, so that all the proofs of the theorem are very easy. This is the way they like to have their proofs. Okay, so this is our fundamental theorem of calculus, right? This is the one we're going to be using most of the time. All right. So before I work a few examples, let me write down just some properties that will be useful. Some of them we've already talked about, and I just want to review them. Others are slightly new. They really all come from just the definition. You don't really need the fundamental theorem of calculus to prove any of those, but you can use it now if you want to. So the first thing, which is the whole motivation for this. So let's assume we have an integrable function, on AB. And that this function is always at least 0 on AB. then this integral, right, what does it represent? This is all what our original picture was based off. You have some function which is integrable on some interval a to b, and it was always above the x-axis. Right? So what is this integral telling us? What did we set it up to compute? The area under the curve, but exactly, but above the x-axis. So this integral represents the area under the curve between A and B and above the x-axis. Probably easier in your head just to have a picture instead of remembering all these words. Important to know. If we drop the condition that it's always greater than or equal to 0, then we said this no longer represents area. So if f is integrable on AB, and then we just drop the second half of the sentence. Right? No and anymore. Then the integral from a to b f of x dx, what does this represent? Let's draw a picture. When my function was just above the x-axis the whole time, then I just got all the area. But if I have a function which does this, okay, we'll say that's my A, and here's my B. Right? When I compute the integral, I get this stuff, and it all has a plus sign. Right? It's all positive area. When I compute this stuff, it gets a minus sign. Right? You want to call it negative area, but of course, it's not. But let's say we just treated this as area, right? You forget that there's a negative sign here, right? You just have a positive amount of area here. Okay? What is the integral computing? Well, it takes this number and it will subtract that number. So this represents the area above the x-axis, right? But under the, I'm going to leave some things out here. Right? When I say area, I'm implicitly saying between A and B and under the curve. So it's the area above the x-axis minus the area below the x-axis. And again, area below the x-axis means area above the curve between A and B and below the x-axis. And of course, this number could be 0, for instance. Right? They could just cancel each other out. So sometimes this could be, something that you're interested in, and then other times you really want the total area. So what would you do if you actually didn't want to just compute this minus that? You actually want this plus this. So you mean find here?
Yeah.
Okay, and once you find where it intersects, right, what are you going to do?
Put a minus sign after the second
You put a minus sign in front, right? If you put a minus sign, then this thing flips over, right? And it becomes positive, and now when you compute the integral, you get the positive area, right? Add them together, fine. So what is that process of, you find it where it's negative, and then you put a minus sign to make it positive? That's the absolute value. It's exactly the absolute value. So, right, if we want all of the area, right, then we can just compute the integral from a to b of the absolute value of the function. So this function, of course, when it's positive, these absolute values won't do anything. They'll go away. When it becomes negative, right, that's when we have something to do. Okay, so what does this tell us? Well, this gives us is the area bounded by the integral AB, the curve, and the x-axis. But it doesn't care whether it's above or below the x-axis. Just any area bounded by the x-axis, it gives it to you. Okay, so later on we'll do examples of that. Okay, now we have a whole bunch of properties we want to write down. So these properties should look very familiar because we've seen them over and over again last term and this term. So first, what happens if I put a constant times a function? Right, well, we know that this is based on a limit. Right? The definition of this is the limit as blah, blah, blah. Sum k times f of x. Of course, what can we do with constants and limits? Right? Well, if the limit exists, we can pull it out. So if we're in a situation, which in our class we always will be, where this integral exists, at least until we get to improper integrals, maybe, then we're allowed to pull out constants. And of course, this was exactly what we could do with the indefinite integral. Right? The indefinite integral is when we're just taking antiderivatives. All the properties are going to carry over. Right? If we had two functions added together, what do you think I'm going to do? Exactly, right? Integral of a sum of the integrals. Probably thinking, geez, these are boring, and of course I already knew these. But these are useful, right? When we actually sit down to work problems, we're going to use this property and this property. We'll use this property constantly. Oh, that's terrible. That is just terrible. Okay, here's one that we've already seen. So here, let's say we start with our integral, and I choose some c in between a and b. Then we know we can break this up at c. Whole is the sum of its parts. That's all it says. Okay. Here's one that will just take you a second to think about geometrically. To assume that your function is always at least 0 on AB. What can you say about the integral of that function? It's always, say it again? It's always at least 0, yeah? Greater than or equal to 0. Remember, this integral, when you have a positive function, is representing the area. Okay? The area, right, under a curve which is positive is going to be positive. Note, however, if you think back to this example that I showed you last week, where you defined a function which was 0 on the irrational numbers and 1 on the rational numbers. Now, that function is always greater than or equal to 0. But, well, under the more versatile Lebesgue integral, when you compute the area, you actually get 0. Okay? But it has all these positive points, and you would think, well, geez, shouldn't you? If it's positive some places, then it probably should have positive area. And the answer is no, it doesn't have to. Of course, in this case, this doesn't cause any problems for us. I mean, for instance, if you made that always greater than 0, you'd expect this to be always greater than 0, right? Doesn't cause a problem for us, though, because that function was not Riemann integrable. So it doesn't cause any problems with our statement. Okay, let's see. Okay, here's a related one. Let's say instead of just choosing f of x as 0, we have two functions. And the g of x is a bigger function than f of x. Right, so that's what we could have. Wherever f goes, g is always bigger. Okay, at least on A. Then, what can you tell me about the area under F versus the area under G? Look at the picture. What can you tell me about the area under F versus the area under G? You must be able to say something.
The area under F is smaller.
That's right. The area under F is smaller. Oh, that's stupid, of course. You thought calculus was supposed to be hard. Math is just the complicated root of turning obvious statements into mathematical formulas. And then the clever application of obvious statements to build non-trivial statements. Like the fundamental theorem of calculus. Okay, let's see, what else? Actually, I don't really want to say the last one on my list because the only use for it is to prove the fundamental theorem of calculus right now, and we already did that. If I need it again later, I'll bring it up. Okay, so let's do some examples. We'll start nice and easy. We'll start nice and easy, but with something that before you knew calculus, you couldn't do. So this here is supposed to represent a parabola, y equals x squared. And, am I going out a little far? Now let's say I wanted to know the area under the parabola between 0 and 1. My first approximation could be this square, which is 1. That's area 1, that is. Okay? That wouldn't be a very good approximation. And then you might say, well, between 0 and 1, you can draw a little vertical or a diagonal line, right? That goes from 0, 0 to 1, 1. That would give you a triangle, right? Which you cut it in half. And now that area is only half. But we know we'd still be getting too much. Right? Okay. But at least we have a reasonable estimate. The area should be less than a half. We want the exact number. We want to know exactly what it is. So, for a good portion of human history, there was no way to do this. Right? They just did not know. Okay, so think of yourselves as being very privileged, right? What a time to be alive. we now have the technology to do this, right? And we don't even need a computer. So the area under this curve between 0 and 1 is represented this way, and it's simply an antiderivative for x squared at 1 minus an antiderivative for x squared at 0. So what is an antiderivative for x squared? X cubed over 3, right? 1/3 x cubed. And the fundamental theorem of calculus says you take an antiderivative, any one you like. Okay? I could put plus 2 in here if I wanted. I don't, but I could. Okay? And then I evaluate it at the endpoints and subtract. Of course, this is very easy. When I plug in a 1, I get a 1/3. When I plug in a 0, I get 0. And so it's a 1/3. Good. A 1/3 is less than a half, so it jives with our estimate. And there's something really cool there. This is... What are the odds that you toss in just this nice curve? I mean, this curve is curvy, darn it, curvy. And you look at the area between 0 and 1, and it actually works out to something as nice as a 1/3. There's not even a pi in it. You think with curves, at least a pi should show up or something. Not even a pi, it's a 1/3. This is nice. Okay. Let's do another example. Let's do one a little more complicated. So we'll first write it and then we'll draw it. So I'm going to integrate on the interval pi over 6 to pi. I'm going to integrate the function cosine of x. Okay, so the fundamental theorem of calculus tells us you have to find an antiderivative for cosine, which would be sine. And then you evaluate it at the end. Okay, so let's see. So this is sine of pi minus sine of pi over 6. What's sine of pi? Yeah, let's see, it's over here, right? And sine is always the height, so height here is 0. That's 0 minus pi over 6, or sine of pi over 6, which is, let's see, remember you had your hand trick. Let's see, so 0, right, is the first one, pi over 6 is the second one, right? And sine's always on the left, so it's square root of 1 over 2, or half. So 0 minus a half is minus a half. Okay, now is this a problem? We tried to compute this area and we got a negative number. How did that happen? Should area be positive? Light shakes his head no. Right? Why not? Direction. How do you mean direction? Ah, okay. Let's quickly graph this thing. Okay, so remember at 0, cosine starts up here at 1. Okay, and where does it hit 0? Pi over 2, right? It's going to shoot down. And then at pi, it's going to hit minus 1. So it's going to go down. Oh, that should be the bottom, right? Okay, and what about pi over 6? That's supposed to be in here somewhere, so it should be about a third of the way over. That's something knocking on our door. Okay, and pi over 6, remember, it's this one here, but cosine's on the right, so it's root 3 over 2. Okay. So we're getting this area up here as positive area, but we're losing this area. Okay, that's negative area. Right? And if you wanted to know how much positive area you had or how much negative area you were getting, what would you do? Well, you could split it up. All right? Integrate this, and that'll tell you how much positive you're getting. If you integrate that, you'll see how much negative you're getting. So what's really nice is we already know the antiderivative. Right? We can just compute this really easily. So for instance, this bit is sine of pi over 2 minus sine of pi over 6. Okay, sine of pi over 2 is, that's 1 up there, minus a half. So it equals a half. So how much area is down here? Right? 1, right? Or minus 1, depending on if you want to talk about the sign. Right? Why is it 1? Well, we know that this was a half, and then when we subtract it, we get minus a half. So we must have subtracted 1. Okay, cool. Let's do another easy. Right, this one should have, yeah.
Wait, so is the answer negative 1/2 or minus 1/2?
So the answer is negative a half, right? That's, I mean, this is all equalities stuff there. So this is if we wanted to break it up and see what things were, right? Then this was a half, and this, right, is minus 1. Now, if you wanted to know the total area, right, and you said, okay, I don't care if it's negative, make it into positive area, then that's exactly what it would be, right? You get a 1 from here, you get a half from here, and the total thing would be 1 1/2. Okay. But if I just state it like this, right, there's no absolute values here, right? I really mean treat this as negative area. Of course, I really shouldn't say that because we don't want to talk about negative area. We just mean treat it as negative. The intuition drove the definition, but the definition is more general than the intuition. I like sentences that do that. Just flip the words around, almost rhyme even. All right, so let's look at a very easy one. This is one you could do without calculus. Okay, so what's the answer? Don't even compute it. Just figure it out. What's that? 1/2. Why 1/2?
X curve, and the slope is equal to x.
Yeah, what are you getting? You're getting the area of this region, which is a nice right triangle. Area of a triangle is the base times the height. Right? Height is 1. I mean, cut it in half, of course, with a triangle. Right? You have a square, you cut it in half. Right? You get half. Okay, so this is very easy. You don't need to do anything. Okay, but we could. So let's do it. Okay, well, the first thing we notice is this. On 0 to 1, the absolute value is irrelevant. Yeah? What does the absolute value do to a number which is between 0 and 1? Nothing, right? So this is just equal to that. And of course, now we can take an antiderivative, evaluate it 1 and 0, and we get a half. And of course, when you plug in 0, it's just all 0. When you plug in 1, you get a half. Okay. Fine. So let's make it more interesting. Let's make it minus 1 to 1. Well, what do I do now? Well, we can think about it again. It should go at the same time. That's a terribly asymmetric diagram for a symmetric situation. What's the area of this other triangle? Well, this one was 1/2, and this is the same darn triangle, right? So it has to have area 1/2, so the whole area has to be 1. So we know this has to be 1. On the other hand, we could compute this explicitly. What is an antiderivative for the absolute value of x? What was the definition? Absolute value of x, right? It's a piecewise defined function. When x is greater than or equal to 0, or when x is less than 0, we get two different definitions. So when x is greater than or equal to 0, what happens to absolute value of x? It's just x. What about when it's less than 0? Minus x. Okay. So if we want to integrate this, it's not surprising that we should get a piecewise defined antiderivative. When x is greater than or equal to 0, or when x is less than 0. So when x is greater than or equal to 0, the antiderivative is just, well, the antiderivative of x. So you get a half x squared. And when x is less than 0, the antiderivative is negative of a half x. Okay. Very nice. So then this thing here is, well, you have to write down what it is. Here's your function. Okay, of course, it looks a little funny. It's not the way we normally write our functions. That's what it is. And we have to evaluate it at 1. We have to evaluate it at minus 1. When we evaluate it at 1, well, that's this half of the function. So x is greater than or equal to 0. So we get 1/2 1 squared minus, well, at minus 1, we're now in this bottom half of the function. So we have to put in minus a half x squared. So it becomes plus a half minus 1 squared. And of course, this is a half plus a half, which is equal to 1. Okay, so it looks a little funny, but at least it gives you the right answer. This is always good. Of course, there's yet another way to compute this. If you don't like writing it down in this way, you could also say this equals the integral from minus 1 to 0. Well, from minus 1 to 0, you know your function is negative x. You get negative x dx. Plus the integral from 0 to 1 of x dx. Right? And now you can play the same game. Okay, the antiderivative is minus a half x squared. You go from minus 1 to 0, and a half x squared from 0 to 1. And now this becomes, well, when you put in a 0, this is just 0. Minus, well, when you put in a minus 1, this becomes minus a half, or plus a half, rather. And then here, you plug in a 1 and you get a half. Plug in a 0, you get 0. So you get a half plus a half, which is 1. Okay, so there's a lot of ways to attack it. Sometimes this feels more intuitive because you don't have to write down all this, but this is shorter because you do fewer calculations. Okay, now let's make one more observation from here. There was something very nice about this function, but not my diagram, which is that it's symmetric. Yeah. So if I know the area of this and I know the area of that, I shouldn't have to compute it twice, right? Now, we had certain kinds of functions which had this property that if you reflect the graph on one side, you actually get the graph on the other side. Right? Or if you like, if you put in the negative of an x, right, put in that one, you get the same value out. Or, to write it down explicitly, if you plug in f of minus x, you get f of x. And you remember what kind of functions those were? And a special name for them. Even functions. So this is if f is an even function. So let's make a very easy observation about even functions. If f is an even function, and let's say it's even at least to some point, right? Maybe just around 0. So we'll say on 0 to some b. Okay, up to some point b is even. Then what is the integral from minus b to b? By the way, when I say it's an even function on 0b, I mean if you plug in f of minus something in this interval, right, you will actually get out the same value as if you've done f of without. Well, we can break this up. We know we can break it up. This is the integral of minus b to 0 plus the integral from 0 to b. But what's the area between minus b and 0 versus the area from 0 to b, if f is an even function? It's the same area, right? Just like over here. Now, with the even function, these give you the same area. That should be minus 1 all along. From minus 1 to 0, you get the same area as from 0 to 1. My picture notwithstanding. So this is actually just 2 times the integral from 0 to b. Now, one reason why you might find that useful is that you can already tell when you get to plug 0 into your function, always seems a little bit nicer. Right? Instead of having to plug in b and minus b, plug in b, plug in 0. Okay? But, we had another kind of function that was kind of nice. Instead of an even function, we had an odd function. Remember what an odd function was? It was one where if you put in minus x in your function, well, you didn't get out f of x again. You could pull the minus all the way to the front. You got minus f of x. Right? Geometrically, that meant you took your picture, your graph, right? You reflected it across, and then you reflected it down. Now what's happening to the area when you do that? Right? We have this nice positive area. You flip it across and then flip it down. All that area becomes negative, right? But it's still the same amount up to absolute value. So what should be happening then? They should cancel each other out. So remember, okay, f of minus x equals minus f of x if f is an odd function. And in this case, the integral from minus b to b, again we'll say f is odd on 0 to b. What should this integral equal?
Zero.
0. It cancels it out. Let's draw a picture. See an example of both of these in action. Let's draw, say, right, there's x squared. This was our first, there's a very nice example, right, of an even function. We already saw what happened if we computed the area between 0 and 1, right, under the curve. And if we want to compute the area between minus 1 and 1, because it's an even function, all we have to do is say, well, this area is the same as that area. That area was a third, so this area must be a third. So the whole area must be 2/3. On the other hand, if we draw an odd function like x cubed, again, let me compute the area between minus 1 and 1. Because this is an odd function, we know that you just take this graph, reflect it across, and reflect it down. So this area is the same as that area. And so if we did the integral from minus 1 to 1 of x cubed, without thinking, we know it has to be 0. We don't have to compute anything. So this is very nice. Let me show you one more cool trick. It has limited application, but I think it's very nice. Let's say we're going to go from 0 to 2 pi. Sine squared x dx. It's already far more complicated than anything we've done. It would seem, anyway. So, if we just want to evaluate this using f-talk, then we would need to find an antiderivative for sine squared. And, well, how did we do that? How do we find an antiderivative for sine squared? We actually did it.
Sin x times sin x. Substitution.
Substitution?
No, that by parts.
By parts, right? You can do it by parts. Okay, fine, we can do that. And maybe we should. But here's something really clever. Think of the graph for sine of x. Okay, nice. Doing this business, right? And then think of the graph for cosine of x. That's this business, right? Are they the same graph?
No.
Almost. They're just shifted over, right, a little bit. And if you go between 0 and 2 pi, that's an entire period, right? Then you basically get the same graph. They're just in different places at the same time, or the same place at different times. Different places at different times. You figure it out. Should the areas be the same? If you forget about, you don't worry about if it's negative, really count as negative. If it's positive, count as positive. Right? Should the area under the sine curve and the cosine curve be the same? In fact, what should those areas be? It should be 0, right? Because everywhere you're positive, you should have a negative. Now, of course, when you go to sine squared, what happens to all those negative areas? They become positive because sine squared doesn't ever go below 0. But of course, sine squared and cosine squared, these are again going to have the same graphs, just shifted from each other. And of course, they're going to encompass the same area if you look at it over an entire period. So what I claim is that this is actually, well, half of what you would get if you went from 0 to 2 pi of sine squared, and you added the integral from 0 to 2 pi of cosine squared. Because these are the same thing, these integrals. Sine and cosine, of course, aren't the same, but if you look at those integrals, they have to be the same. And so if you add 2 of them, then you get twice as much, so you have to get rid of half to get back what you want. But I have 2 integrals. Right? Integral of a sum is the sum of the integrals, or it's backwards, right? Sum of the integrals is the integral of the sum. So this is 0 to 2 pi sine squared x plus cosine squared x dx. Of course, what's sine squared plus cosine squared? 1. Just 1. A half integral 0 to 2 pi dx. This is a much easier integral. Antiderivative is x, so. Of course, when you put 0 in, you're going to get 0. You put 2 pi in, you're going to get 2 pi over 2. Neat.
That's what I didn't know.
This part here?
Yes.
Okay, so again, this integral and this integral are the same. Think of the curves. Okay, just start with sine of x and cosine of x in your head. Okay, they're the same curve, so they must give you the same areas. Right? They're just moved around, but it doesn't matter. The areas stay the same. And when you square things, that's not going to hurt. Right? The sine squared curve and the cosine squared curve are still the same curves, just again shifted from each other. So when you compute the area over an entire period, this would not be the same if I went 0 to pi. And if I went 0 to pi, things would be really different because you wouldn't be getting an entire period. Right? You wouldn't have exactly the same regions. But this ensures that you get all of the behavior. Okay, so these are actually the same thing. So what I really have is 2 of these. Of course, then I have to multiply by half, and now I have 1 of these. And from there, it's, as I say, academic. Don't stress about this one too much. I just think it's a nice trick. But what it suggests is, given that finding antiderivatives is not always the easiest thing. And at this point, what's easier, derivatives or antiderivatives? Derivatives, right? No question. I can't give you a function that you're not going to say, well, okay, it might be hard, but I know what rules to apply here. Okay, with antiderivatives, I can give you functions you have no idea what to do with. Right? Very easy to come up with those. Right? Okay, fine. So what does that tell you? Well, it tells you if you need to compute an integral, right? You want to know a definite integral. I don't know if I said this explicitly, but if you don't have the bounds, right, then we just call it an indefinite integral. As soon as you add these limits of integration, computing these areas is called a definite integral. Okay. If you want to do that, try to think as much as possible about how you might do it without actually finding an antiderivative, right? Before you actually have to go. I mean, if you already know, if it was just a sine of x, right, or cosine, then you know what the antiderivative is. No problem, just fire away. Right? But something like this, where you have to do a little bit of work to compute the antiderivative, or something even worse, like like this. Okay. All of a sudden, this gets tricky. No? It can get very tricky. So you have to start thinking, how could I attack this without finding an antiderivative, right? Is there a nice, subtle, easy way to do it like this? Can I say, knowing something about the function, does that help? These limits, by the way, are not interesting limits. The function is interesting, the limits are not. Okay. What do we? So, yeah, we did that. We did that. Okay, so next time, I want to really start it now. I just want to tell you what we're going to do. Next time, we're going to start looking at this sort of situation. Let's say I have two functions, and they create a region in between them. How do I attack this? How do I get the area there? And the answer actually would be pretty easy, but we'll work a couple examples.
Do like the volume thing.
Yeah, so
The
eventually we are going to have to see something about volume.
I got donuts in my class for doing that.
You got donuts.
Yes.
So you're going to bring in donuts for us?
No.
Are we going to learn the different methods? Like the shell method and then the disk method?
You don't want to.
Oh no, I just don't like the shell method.
You don't like the shell method, but the disk method is okay?
Yeah.
And the washer method, and the pancake method, and the...
Well, it's a big all.
I like French toast, actually. This weekend I put a little ricotta cheese on it and some maple syrup. Good stuff. Good stuff. Yeah, we're gonna get to touch on all these things.